So far we have seen the different functionalities which basically add the new value at the end of the single linked list, and which will basically add and remove the new values in front of the single linked list, right? And we have also implemented get functionality on a single linked list. Now that combining all these functionalities, we can write the insert operation on a singly linked list. So insert operation, what exactly it does is, it is basically used for inserting a new value anywhere in the singly linked list. For that operation, what exactly we will do is, we will basically take the index from the user and will also take the value that user wants to insert into the singly linked list. So here our job is to make sure that we are inserting a new node with the value that user has passed at the given index. So that is the main aim of the insert operation on a singly linked list. So remember that we have to take the index and we have to take the value, and we have to make sure that the new node with whatever the value that user has passed, we have to make sure that we are inserting a new node at the index that user has passed. So obviously, just like any other operation that involves index, right? The possible ranges for the index are basically, in the case of single linked list, are from 0 to length of the single linked list minus 1. But here there is a catch. The valid index for insert operation is from 0 till length of the linked list. Why? Because if you consider the single linked list that we have here, right, the indexes are 0, 1, 2, 3, 4, 5. But inside this single linked list, we almost have 6 values. That means the valid indexes are from 0 to 5. But the thing is, if the user passes an index 6, right, that means that we can insert a new node at the end of the singly linked list. That's why for insert operation, the possible range of index that user can pass is actually from 0 till the length of the linked list. And obviously, since singly linked list can store any type of the value in it, there will not be any validations on the value that user is passing. So the only validation that we have to make sure is if the index that user is passing is in the range of 0 to length of the linked list or not. Okay, so that is the basic definition of a insert operation. Now let's go ahead and let's try to understand what are the different cases that could arise when I try to implement the insert operation, and what are the functionalities that we can reuse for implementing the insert operation. So the first check would obviously be to check if the index that user has passed is invalid index or not. That means that when we are taking the index from the user, right, index is nothing but an integer value. So user can pass any negative values, and user can pass values that are greater than the length of the singly linked list. Obviously, in those cases, we will not be able to insert a new node into the singly linked list, right? That's why, as part of the first check, we will basically check if the index that user has passed, if it is less than 0, or if the index that user has passed is greater than the length of the linked list. If this is the case, we will simply return false, indicating that we are not able to insert the new node into the singly linked list. That is the first case. So besides this invalid case, all other indexes whatever we get from the user are basically valid cases, right? Out of those valid scenarios, the first scenario is if the index is equal to 0, right? The whatever the index that we are getting from the user is 0. That means that we already have a value at index 0. That means that when user asked us to perform insert operation at index 0, user is literally telling us that, insert a node before the existing head node, right? That operation is nothing but unshift operation, right? So we have already implemented this unshift operation, and we tried implementing it in such a way that it will handle all the scenarios already. That's why if the index is passed by the user is 0, what we will do, we will simply call the unshift operation with whatever the value that user has passed. So it will make sure that it is inserting a new node at 0th index. 0th index is nothing but before the existing head of the singly linked list. Let's assume that the value that user has passed is 10, right? So in that, let's say, again, let's assume 10 only. Now, unshift operation will make sure that it is inserting a new node, and head node also will get updated to the newly added node. So that is the first scenario when the index that is given by the user is 0. And as part of the third case, basically it is the second case where, let's say, the index that is given by the user is equal to the length of the linked list. That means that the last node is at the index length of the linked list minus 1, but the index that is given by the user is equal to length of the linked list. That means that we have to insert a new node after the tail node. That is nothing but a push operation that we have already implemented. In that case, if the index is equal to length of the linked list, what we will do, we will simply call the push functionality with the value that user has given. Let's assume that the value that user has given is, let's say, 1000 or 100, right? In that case, what exactly we will do, we will simply create a new node with value 1000, and we will adjust the next pointers of the current tail node, and we will update the tail node to the newly added node. Now if you see here, the index of the value 1000 will be 6. Okay, because we altogether have 7 values inside the single linked list, and the value 1000 is at the index 6. That's why you have to make sure that you are taking the valid values of the index from 0 till the length of the linked list. Okay, so that is the second scenario when the user, whatever the index that user has given, is the last index of the singly linked list. Now let's just try to understand if the index is any other index than 0th index, or the index that is equal to length of the linked list. That means that user wants to insert a new node with whatever the value after the index 0 and before the very last node we have on the singly linked list. So in that case, what exactly we will do is, we will try to reuse the functionality of the get functionality. But before I go ahead and I explain you the algorithm, right, let's just try to understand how the insertion actually happens. Let's assume that we have, let's say, 4 nodes inside our singly linked list. So the index will be 0, 1, 2, 3. Let's say the values are 10, A, C, let's say D are the values we have inside the singly linked list. And we have the head node and we have the tail node, and each and every node is connected to the next node like we have inside the singly linked list. Now here, as part of the insert operation, what I have actually given is, I want to insert a value at the index 2 by the value AB. That means that right now the index 2 has the value C, right? Now we have to make sure at the index 2 we are inserting a new node AB. That doesn't mean that we actually have to update it. We may have to make sure that we are inserting a new node altogether. That's why what exactly we will do is, with whatever the value that user has given, right, we will create the new node, and this node should be available in its before node, right? That means since we are inserting a node at second index, this node's reference should be available at the node that is at index 1. That means that next of A should store the reference of AB. Similarly, the next of AB should store the reference of C. In this way, this connection will be broken and new connections are being established. As a result, this AB will be available at index 2 and C will be available at index 3 and D will be available at index 4. So what exactly you have to observe here is, to insert a new node, first we have to have the nodes that are available at index 1 and the node that was at index 2 before we inserted the node, so that to the newly created node we can adjust the connections. If we generalize this, right, let's say if I am trying to insert the node at kth position, we have to have the node that is available at k minus 1th position and kth position, so that whatever the new node that we are inserting, we can adjust the next and next of the next nodes clearly. So in this way, to reuse the already implemented functionalities, what exactly we will do is, to have the access of this k minus 1th node, we will try to reuse the get functionality. Once we get that k minus 1th node, we will have the kth node also by simply doing dot next of k minus 1th node, and we will have a newly created node, and we can simply adjust the next pointers very easily. So that is the algorithm that you can use when the index that is given by the user is anywhere after index 0 and before the length of the linked list minus 1. So that is the otherwise index is greater than 0 and length of linked list. If this is the case, what we will do, first we will get the k minus 1th node. Once we get the k minus 1th node, this is k minus 1th node. Now the kth node will be this k minus 1th node dot next, right? Now with whatever the value that user has passed, we will create new node to it. Now this k minus 1th node next should be this new node that we have created. That's why k minus 1th node dot next will be equal to new node. Now we have adjusted the connection for the newly created node. Now to this newly created node, the next should be whatever the kth node that we had previously, which is available inside this kth node variable. That's why to update the next, new node dot next is equal to kth node. In this way, we are actually inserting the new node into the singly linked list. Just remember that this is not the update operation. We will have to insert a new node into the singly linked list. At the same time, we have to make sure that none of the values are getting lost while performing the insert operation. So for that simple operation is, these are the different cases, but this is the specific case where user is trying to insert a new node after index 0 and before the length of the linked list, whatever the index that user can pass. Okay, all right. Now let's write the logic for performing the insert operation on the singly linked list that we are implementing. So previously we have implemented couple of the inserting new value related operations, which are basically push and unshift. Push basically adds the new value at the tail of the singly linked list, and unshift operation basically adds the new value in front of the existing head out of the singly linked list. But as part of the insert operation that we are going to implement, user can pass any index at which they want to insert the new value. So basically user will be passing the index at which the new value needs to be inserted. So here the return type that I want to use is boolean. Based on whether we were able to insert the new value at the given index or not, we want to return true or false. And let me just name the function as insert, and this function will basically take the index from the user, and it will also take the value that user wants to insert at that specific index. Okay, now obviously whenever user is passing the index to us in a function argument, right, we know the valid indexes are from 0 to, on an existing singly linked list, valid indexes are from 0 to length of the singly linked list minus 1. But for inserting new value, the valid indexes are from 0 to length of the linked list, because user can still insert a new value after the last index whatever we have. As a result, for this insert operation, valid indexes range will be from 0 to length of the linked list. So that is something that you should never forget. As part of the first case, let's just try to honor the invalid index given by the user. So if at all the index given by the user is less than 0, or if the index given by the user is greater than the length that we have on the singly linked list, then it is an invalid index. Obviously at these indexes inserting the new node is not possible. As a result, we will simply return false. Okay, so that is the first case. And the second case is, what if the index given by the user is 0? That means we already have the head node at index 0, but user still wants to insert the new node at index 0. That means user wants to add new node in front of the existing head node. That operation is nothing but unshift operation that we have already implemented, honoring all the scenarios. So if the index given by the user is equal to 0, what we will do is we will simply hand over the logic to unshift operation that we have already implemented. So we will simply call this dot unshift and we will pass the value that user has passed. So it will automatically add the value in front of the existing head node. In the end, since we are able to add the new node, we will simply return true. Okay, second case is also handled by reusing the logic. Now one more check is there where we can reuse the logic. If at all the index given by the user is equal to the length of the linked list, that means already last index is length of the linked list minus 1 where the tail node is there. After that the index is equal to the length of the linked list and user has passed that index. That means user wants to add the new node after the existing tail node. So in that case we can simply reuse the push operation that we have already implemented. So if at all that index given by the user is equal to the length that we are keeping track on the singly linked list, what we can do, we can simply call the push operation by passing whatever the value that user has passed. As we are able to add the value, we will simply return true in the end. Okay, so far adding the new nodes at index 0 and index equal to length of the linked list are handled. Now what if the user passes any other index after 0 and before the last index that we have on the singly linked list? So now let me just give a small example, right? Let's just say I want to insert a node at index 3 where I already have 5 values on the singly linked list. So if I want to insert the new node at index 3, first I should go to the node at index 2 such that whatever the new node that I have created from index 2's node, next I can update the new node, and from the new node whatever the next nodes that are there that I can assign, so that the entire singly linked list will be safe. We would have also inserted a new node at that specific position. So the first step is to get the node before the index that is given by the user. So here let me just read the node before whatever the index that user has passed. So let me just do node start and let me just read it into one variable called node, and to get the node before the index that is given by the user, I will simply want to reuse the get function that we have already implemented, and this dot get of whatever the index that is given by the user minus 1. Here one more doubt you might get is, this get function we have written for invalid indexes also, right? But our logic will never go into this invalid indexes, because if the user passes an invalid index to insert operation, as part of the first check itself we are returning the false. So our logic will never come to else block if the user passes an invalid index. So we don't have to worry about handling the null check in the insert operation after getting the node, like we have handled in the case of set operation. So that is something that you can remember. Now along with this, I also want the next node that we have from this node that is at index minus 1th position. So let me just say next nodes equal to node dot next. Okay, now here I think I need to use the arrow. Okay, so I have the node at index minus 1th position. I have the nodes that are available at indexed position as well. Now what I need to do, I need to insert a new node with this value at indexed position. So what I will do first is, let me just create the object of node first, and this will be new node equal to new node of type whatever the value that we are passing, and we just need to pass the value to this object creation. Now This node is at index minus 1th position. This node should go on to indexed position. For that, what we will do is node dot next will be equal to the new node that we have created with whatever the value that user has passed. Before adding this node, whatever the next nodes that we had after this next should become the next of the newly created node. That's the reason why we will do new node dot next is equal to next nodes that we have read. As a result, we have also inserted the node at index position, and we have adjusted the next connection such that we have the access to the entire singly linked list. As we have added one more value into the singly linked list, here we need to increment the length by 1. So we should never forget that. In the end, as we are able to add the new value into the singly linked list, we will simply return true. Okay, so that is the logic for inserting a new node at the indexed position where the index given by the user is greater than 0 and less than the last index that we have. Okay, so we have implemented the insert operation honoring all the cases by reusing whatever the functionalities that we already have implemented. Now let's just test this out. So let me just comment out all these get calls and let me just call the insert operation. Now we already have 3 values on the singly linked list, right? So if I perform the insert operation, let's just say I want to perform the insert operation at index 4 and I want to insert 100. So index 4 is invalid index for insert, right? So the valid range for insert operation is from 0 till the length of the linked list. Here we have 3 values, so valid indexes are till 3, but here I am passing 4. So ideally this should never get inserted. As a result, basically it should go on to this invalid indexes logic and it should return false. So if I perform the traverse after inserting also, we should not see any difference at all. That means we should see 0, 10 and minus 10 only, both the traversals, and that you can see on the console as well. Okay, so if at all if I pass an index 3, so I am trying to insert the value at index 3, right, which is equal to length of the linked list. So it will go on to this one and it will add the value after the existing tail node. So output should be 0, 10, minus 10 and what is the value? 100. So that is the second traverse output should be. See, that is what we have got. So similarly, you can pass any valid index. Let's just say I want to insert 100 at index 1. We already have 10 at index 1, right? So if we insert 100, the resulting linked list will be 0, 100, 10 and minus 10. So whatever the values we already have at index 1 will be moved to plus 1th index position. So index 1, whatever we had, will move on to index 2, and whatever the index 2 we had will move on to index 3. So if I run this, 0, 100, 10, minus 10 should be the output. So that is what we have got here. So if I pass any values, I can pass index 0 also, right? If I pass index 0 already has 0. So if I insert this 100 there, 100, 0, 10 and minus 10 should be the output. And see, that is the output. Okay, if you pass any negative value, it will go on to invalid indexes and we should not see any change at all. So that basically concludes that we have successfully implemented the insert operation according to the index and value that user has passed, and we have validated all the cases as well, as we have seen on the console. Okay, now that we have implemented the insert operation, let's just try to analyze the time complexity and space complexity of the algorithm that we are following for inserting a new node into the singly linked list at a given position by the user with whatever the value that user has passed. And this also, let's just try to divide and analyze in best case as well as worst case. Okay, so when will the best case of insertion operation will occur? Let's assume that we have some number of nodes that are available inside the singly linked list. So as part of the best case is something that it will simply occur with a simple update operation. So in the case of insert operation, whenever the user is trying to insert a new node in front of the existing head node, that means that at the index 0 itself, that is a simple update operation. Because we already have the head node, we are simply using a unshift operation performing the same insert. Similarly, if the user, whatever the index that user is passing, if it is the index that is equal to length of the linked list, in that case we are simply reusing the push functionality. In these two scenarios, since we had the access to the head node and tail node, with the simple update operations, we were able to add the new node into the single linked list. As a result, that is the best case of a insert operation on a singly linked list. In that case, obviously both unshift as well as push operations will take only constant amount of time. So we can say in the best case scenario, the time complexity will be order of 1. Now, when will the actual worst case scenario of the push functionality insert operation will actually occur? Let's assume that we have some number of nodes available inside the singly linked list. Here, let's assume that there are n number of nodes. So this is the head node and this is the tail node, index 0, 1, 2, 3. Now, just assume that this is the nth node. Now, let's assume that whatever the index that user has passed, right, if it is equal to the n minus 1, so we already have the n nodes available in the singly linked list, and the index that user has passed is n minus 1. That means that user wants to insert the node at the very last index in the singly linked list. In that case, we have to call the get functionality by n minus 2, right? In that case, to get the node that is at n minus 2th index, we have to run a loop for n minus 2 number of times. So in that case, that's why the worst case time complexity will be order of n minus 2. We can simply say order of n. Now let's just try to understand the same thing in terms of space. So if you already know when is the best case, right? When the user is trying to insert the node at the beginning or at the end of the single linked list, that is the best case scenario. In both those scenarios, we will simply reuse the unshift and push operations, which will basically make the necessary adjustments in a constant amount of memory. If you remember the time and space complexities that were involved in the push and unshift operations, right? They were constant. As a result, in the best case scenario, the space complexity will be order of 1 only. Now let's just try to understand the space complexity involved in the worst case scenario. Here altogether we are calling the insert operation at the index n minus 1, right? And we are making the reuse of the get functionality. And if you remember the time complexities and space complexities involved in the get functionality, right? We will simply reuse a single variable for reaching the node at any position in the singly linked list. As a result, even in the worst case, the get functionality will have a space complexity of order of 1 only. And once we get the node also, after that, we are making 2 next pointer adjustments, right? And these next pointer adjustments will obviously be a simple assignment operations, and they will take only constant amount of memory. As a result, the overall space complexity in the worst case scenario of insert operation on a singly linked list, where you are trying to insert the node at the very last index, will be order of 1 only, even in the worst case scenario. Okay, so that is the time complexity and space complexity analysis of a insert operation on a singly linked list.